Assalamu alaikum and greetings. Text of this task is a rectangle contour is given with dimensions b and c. So we have a rectangle contour with dimensions b and c placed as shown on this picture in the way that is parallel with the infinitely long conductor. So it is a parallel to the infinitely long conductor with current I. Determine flux through this contour I and magnetic forces on each side of the contour. And also a coordinate system is given where this is z-axis, this is y-axis, and this is x-axis. Very important thing. So this is rectangular, it's only drawn, this 3D problem is drawn on a table on 2D. What is this actually? This is, I have infinitely long conductor, which is this, and parallel to this conductor is my rectangular area surface, which is this. So we need to calculate a flux. How do we calculate a flux? Well, we know that the flux is B times ds. So we need to calculate flux for this contour. In order to do that, we will firstly draw ds, some ds. So this would be our ds, infinitely small surface, ds. What its direction? Its direction is, because we have directed contour, it is determined with right hand rule, where we can see that direction is up into the z-axis. So this is our ds. It is a normal to this. But now we need to calculate our magnetic flux density. So because of that, I will draw, in order to calculate our magnetic field B, we know that magnetic flux density for an infinitely long conductor is μ0 times I with 2 pi times d, where d is the distance from the conductor which creates its magnetic field. But what is that difference? Well, here we have our ds, which means we need b. In this case, we will draw this one case at this point, and its distance is, well, I drawn it really. So this is d. This is our distance. But what can you notice is that this our distance, when we come to this ds, so we will now move, and in some case we will get that ds, our ds is this. And in this case our ds would be our distance of magnetic field would be this. And as you can see, this all makes an angle, some angle alpha, and also here we will say that this is also alpha. But as you can see, when I'm analyzing this small surface, I have one distance d and angle alpha, but when I move this surface a little bit right or left, my distance changes, and also this angle changes. It's not the same. So b is not a constant, it depends, it's a variable, because its distance is changing, and also this angle is not a constant. But how can we write it then? Well, we usually have the distance, I have a conductor on this distance, I have a surface, I need to calculate ds here, this is on distance x. So if I need a magnetic flux density here, magnetic flux density would be 2 pi x. and we choose this coordinate system, but we have a 2D system, we have surface, and but here we have a little bit more complicated three-dimensional system, where our surface changes in the y-axis, not in the x-axis, like here. Actually, we now have here y-axis, so this is actually y, which means, for example, this infinitely small part will be dy. So this distance here from the coordinate systems is y, and this infinitely small part here is dy, because now the y is a variable. We will write everything as a function from y, which means this distance is actually, this here is y. And now if we know that our variable is y, and we need this distance, we have a right triangle here, we can calculate our distance is actually a hypotenuse, so we can calculate it, and we know that the hypotenuse is equal to the square root of one cathode, which in our case is this A, represents the parallel of this surface, plus the other cathode, which is y. So that would be it. But what is the direction of our magnetic field? Well, for now we have that ds is a normal to our surface, and it creates an angle of 90 degrees compared to our surface. Our magnetic field, this makes circles, which means, and this is the direction, using right hand rule, so this is the direction of circles, and at this point, because it is not, my conductor is here, and if this point was here, then my circle would be a tangent and would have this direction, but I need here, so my circle here, the tangent is actually this B. And as I said in the many previous videos, the tangent of a magnetic field and this distance from a conductor, it always creates a 90-degree angle. Which means that now here I have some angle beta. So I have found what is my B, what is infinitely small area. Well, now this is infinitely small area. What is its base? Its base now is not dx, it is dy times its height. What is its height? Well, it is c. So, in order to calculate my flux is b times ds, but dot product of two vectors. And we always had that the angle between these two vectors was mostly 0 or 180 degrees. But this is actually b times ds times cosine of angle between b and ds. So, in order now to calculate our magnetic flux, we need this angle between b and ds. But what is this angle? We can determine it really simple. Why? How? Well, here you can see we have this. This is 180 degrees. 180 degrees is this. So we know how to calculate alpha. So it's very important to write this angle as a function of alpha. So this is 180 degrees is alpha plus this is 90 degree and plus beta. So from here we can see that alpha plus beta is 90 degrees, or p.5. But what does this mean? It means for every part here, alpha plus beta is 90 degrees. But where do I have 90 degrees? I have a 90 degree here. As you can see, ds and this is 90 degrees. So if this is beta, it means that this is alpha. Why? Because alpha plus beta is always 90 degrees. And now when I found alpha, I actually need cosine alpha. So I will write this as a cosine alpha. So my magnetic flux is equal integral b is me 0 I 2 pi square root a square plus times ds is c times dy, so it is c times dy, I will write dy the last, and times cosine alpha. But what is cosine alpha? I'm looking, where do I have right triangle? I have it here. What is cosine alpha? Well, cosine alpha, I know that it is adjacent side, which is in my case y, divided with the hypotenuse, which is d, or which is square root as a square plus b square. So I put this here, and I will get that this is y square root a square plus b square. What are the borders? Well, as you can see, my surface starts from the center of coordinate system, which is 0, and it goes to the b. So our flux is equal, everything that's constant I can put it in front, draw it in front of integral. What will I have? Square root of this times square root of this is a square plus y square with the y dy. You solve this integral with simple substitution. You know how to solve integrals. I'm guessing that you know. And when you solve this integral, you will get that flux is equal to the me 0 I psi 2p times 2 natural logarithm a square plus b square with a square. So this is flux. In the next video we will show you how to calculate a force. Now we will calculate our forces on each part of our conductor. So we will have 4 cases. This will be the first case, this side will be the second, this will be the third, and this will be the fourth case. We know this conductor creates this magnetic field which has this direction, which are circles and etc. How do we calculate the forces? Well, if you use as a vector, it is, and if magnetic flux density is constant through all the length of conductor, then we can use that F is equal I1 times L, the length of conductor, cross product times B, or if B is not constant through the whole length of a conductor, then we use the integral form, which is dl, integral of dl cross product B. Or if we want to only calculate identity of this vector, which we need to do. Our force F is equal I times L times B. Cross product of two vectors is sine angle between these two vectors. So our first case is this here. So what do we have? This length. Firstly, what we can notice is this conductor is actually this, and this is parallel to this. So we have a surface, this is parallel to this. And now this side is actually this side here. So it is actually this side here. Which means through all of its length, they are parallel, here, here. So this conductor is on the same distance and it's parallel. Now what we need to do is to determine the angle between B and and L. So we know that L has a direction of a current. So this is DL or L. Here, also here, DL, also here, DL has the same. But we need to find a direction of our magnetic field also. Well, because it is a parallel, this conductor creates the lines of magnetic field here, and because this point is parallel, it would be the circles, but here it is a tangent and it is actually this case. So it would be a circle around this conductor, but here it's a tangent. So what angle is between DL and this? Well, this is a rectangular, so DL here is 90 degrees. But also what we need to calculate our magnetic flux density. B is equal to 0 for infinitely long conductor on some distance, 2 pi times the distance. What is the distance? Well, because these two conductors are parallel, we need at this point, it means the distance is actually this A. So we put that in here. Sine angle between these two is P and a half, 90 degrees, and we know that sine of 90 degrees is this. So we will get that our first force F1 is equal I1 times μ0 I 2PA times the length of our conductor, which is C. But now what we need to do is our second case is this. So what we need to do is, now once again we have our infinitely long conductor, and now we have this conductor. This is actually once again a conductor on distance this, and at every point of space they are on the same distance, which means the magnetic flux is constant through all of its length. So we will draw only one case. So this is the case. What is the direction of magnetic flux? Once again, these are the circles, but here, because it is not really parallel, it is a tangent. So this is B2, this is D, which is distance. Here is angle 90 degrees. As we said, that the angle between this distance and the tangent is always 90 degrees. So our magnetic flux density in this case, which is the second, is μ0 I 2 pi times the distance. But here the distance is, we have right triangle, and D is the hypotenuse of this right triangle with cathets A and B, which means this is A squared plus B squared. Now, we need L, length. Length is once again this, which is C. And we need angle between L and B. Well, what is this? This is actually, as I said, this conductor and this conductor are parallel. And we have, this conductor creates magnetic field, these are the lines, this is the tangent of a magnetic field, but this is the conductor. Only directed from the table towards, because the current goes from the table. This is actually like I'm looking at this. This is I1, this is DL. It goes from the table, from you to the table. So, if this is magnetic field here on this surface, and the conductor is this or towards the table, the angle is 90 degrees. Once again, the angle is 90 degrees. Actually, what do I have? Well, this is my DL, the current. It goes from you to the table, and this is my B. So, it has this direction. But here, it's 90 degrees once again. What happens if I was at this point or this? Only this angle would change. So this would change, this would rotate. But at every point, the angle between these two would be 90 degrees. So once again, here the angle is 90 degrees, which means sinus is 1. So our force F2 is I1, mu0, I, 2 pi square root square plus B squared times C. But now the harder part comes. F3 and F4. What happens here? Well, let's take this. Now we are analyzing this side. This is our third case. So, what do we have here? Well, as you can see, this is DL. And this is the distance, D. But as I'm walking through this length of a conductor, this distance D changes, and it creates some angle alpha. And what is my magnetic field? Well, magnetic field is a normal, it is a tangent to this point, B, which is B. This is B3, and it has an angle of 90 degrees. The tangent towards this distance has an angle 90 degrees, which means this is some angle beta, and because DL has this direction, my B is a tangent, has this direction, it means that beta is actually the angle between B and DL. But now what happens? As I'm moving through the conductor here, I have a different distance of magnetic field, and I have a different angle alpha and beta, etc. So, now I cannot use this formula because this is if my magnetic flux is the same through all the length, but now it's not because the distance from our conductor changes. So our B magnetic flux density is mu0 I 2 pi times the distance. But now the distance is once again, what do we have? dl, because this changes in the y axis. Our dl, infinitely small part of the conductor, is actually dy, because we are moving alongside of y axis. So this here is y. It means that distance is the hypotenuse of this right triangle with cathets A and Y. The same thing as in previous when we calculated flux, which means this is a square plus y square. dl is equal to dy. And now we know that the angle between B and DL is beta, but we need to determine what is beta. Well, we can, very simple, we can see that this is angle 180 degrees, which means, and this is 90 degree, which means alpha plus beta must also be 19 degree, or p and a half. From here, beta is p and a half minus alpha. So our force F would be I1 integral dl times b times sine of angle between L and B, which is p and a half minus alpha. So I will put everything a little bit, just change the order. So this is F3. It will be firstly B mu 0 I 2p square root a square plus b square times dl will be last. But what is sine p and a half minus alpha? Well, we will determine that. We need to write it as a strictly function of alpha, because we can calculate what is sine or cosine alpha. Well, sine p and a half minus alpha, you must remember the trigonometric formula, identity. This is sine alpha minus beta, which is equal sine alpha times cosine beta plus minus cosine alpha times sine beta. So here we will have that this is sine p and a half cosine alpha minus cosine p and a half sine alpha. We know that cosine of 90 degrees is 0. We know the sine of p, so this will be equal to 0, is 1. So it means that this is actually cosine alpha. So I can write this as cosine alpha. But what is my cosine alpha? Well, from here, cosine alpha is adjacent side, which is y, divided with its distance, which is the hypotenuse, which can be calculated as a squared plus y squared. So, and what are the limits of this integral? Well, my integral starts from the center and it ends here, b, from 0 to b, when we are looking y-axis. So we put this here, and we will get the same integral as when we calculated the flux. So we will get that F3, its identity is mu0 I times I1 divided 4p natural logarithm a squared plus b squared divided a squared. And then what did we left? Well, we only have to calculate this fourth case. So here, but what is the difference? The difference dl is this. This is the distance from the conductor. It will create once again a magnetic field. This is the distance d. It creates some angle here alpha, but the magnetic field has this angle, and this is B4. It will have exactly the same formula. So B4 is mu0 I 2p 2 pi. The distance is, once again, we have y. This is A side. So we will have the same thing. dl is dy. But what changes? Only that changes, F4, is this, the angle. So now dl, because it is directed, it is in the direction of the current. Now angle between dl and b is this. So I will write it down here. So the angle between DL and B is this, which is alpha plus 90 degrees. So what will we have here? That F4 is sine angle between these two, but the angle is alpha plus 90 degrees. What is equal to the alpha? Sinus alpha plus 90 degrees. Once again, using the same formula as we used, the trigonometric formula function in the previous video. This is sine alpha cosine p and a half plus cosine alpha sine p and a half. So cosine p and a half is 0, so this all will be equal to 0. Here sine p alpha in 0 is 1, so only what will be left is cosine alpha. So once again I will get cosine alpha here, so this is equal to the cosine alpha. And what is cosine alpha? Once again, cosine alpha is the same as here. So it is adjacent side divided with the hypotenuse, which is a square. And you will get the same result. Only what changes is the direction. So if you want, you can determine the direction of forces on every part using right-hand rule, or calculating this as a vector product using determinants and such. So that would be it. Thank you for watching. See you in the next video.